Okay, so we want to now go on to speak about having done the linear search. We want to go and speak about the concept behind a binary search. So we want to talk about the binary search, and the binary search requires us to actually know how to sort information. Okay, so the first thing that I'm putting down here is that the binary search requires a sorted, and I'm underlining sorted, list of values. Okay, and the next major thing that I'm going to put down here is that the binary search, it takes a divide and conquer approach. It takes a divide and conquer approach to searching a list of values. So these are the two major things that you need to know about the binary search. Okay, the binary search, it requires us to have a sorted list, and it also requires us to take a divide and conquer approach. Now, we don't know how, or we haven't officially learned how to sort values using sorting algorithms, and we will look at next class two different sorting algorithms. The bubble sort and the selection sort. But for now, we will just work on a list of sorted values, okay? So let me just give you all a little definition of the binary search. Or actually, no, let me describe the binary search to you, and then we will define it in terms of some sort of hard definition. So let's say, for instance, we have a sorted list of values, right? 1, 2, 3, 9, 14, 18, 19, 21, 27, 29, 35, 36, and 40. All right, so we have a sorted array of values. I'm just going to put some lines between them. And we have some index positions. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Values. All right, I dropped off there for a second. We have 13 values inside of this array, and we want to use the binary search approach to solve this, to find a value inside of here. So anybody, give me a value that we want to look for inside of this array. Let me hear Jasmine. Give me a value that we want to look for. No, nothing from Jasmine. Jiran?
27.
27. So our search key, right? So our key value is 27. So how we start with this is that we will start by marking the position of the start value in the array and the end value in the array. And we will add the positions of the start value and the end value and divide it by 2 to get the middle value of the array. So 0 plus 12 is 12, divided by 2 is 6, okay? So this is the middle value of the array. And then you compare the key value against the value in the middle value. Is the key value bigger or smaller than the middle value? The key value is bigger. Okay, you know what? You know what this class like right now today? I feel like I'm hosting an episode of Jasmine, I saw your message late. I feel like I'm hosting an episode of Blue's Clues or something so. Right? Like when when Steve used to go, you know, do you see a clue? And then pause. And nobody's talking, but then he's like, yes, we see. Joshua, you don't know what Blue's Clues is? Blue's Clues, like with the little dog. All right. I see somebody shocked, so yeah. All right. One day, maybe one day we can run an episode of Blue's Clues for Hazard. All right. But I feel like Steve from Blue's Clues, okay? I ask a question and then I end up answering it myself. Anyway, 27 is larger than the middle value. So what does that mean? It means that there is no way, because this is a sorted array, there is no way that the value of 27 is anywhere inside of here, right? Up to this value. So what does that mean? It means that now we assign a new start value to here. So we cross out the old middle value and the old start value, and we put the start value here. Because we now know that the only potential for finding that search key is inside of this second half of the array. So we say, okay, the key is 27, the new start value is 7, 7 plus 12 is 19, 19 divided by 2 is, 19 divided by 2 is, as an integer, that would be 9. Okay, so this is now the middle value. All right, this is now the middle value. And we compare the key against the middle value. And now the middle value is larger than the key. So what does that mean? It means that we can't find any of them inside of here or here. So we now make this end value to be the one before the middle value. Okay? And so now we have the start and the end value. And again, we'll add them up. 7 and 8 divided by 2. 7 and 8 is 15 divided by 2. The new middle value, 15 divided by 2 is 7. The new middle value is here. And so we are comparing 27 against 21. And what happened here is that we can't, of course, we know that the key is bigger. So it's not this value. We make the new start value here. Okay, and we'll make the new middle value here as well, because the end and the start is the same thing. So the end and the start, 8 and 8 is 16 divided by 2. This is the middle value, and this is where we find it. Now, this seems like a lot of work, but it's not, because we found the value in 4 steps. We found the key in 4 comparisons. Whereas, if we had to use a linear approach here, it'll take 9 comparisons before we could find the search key, right? We'll have to compare 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, because we started at position 0. So this is actually a quite effective way, because you could rule out large sections of values inside of your searches. Everybody's with me on this?
Yes, sir, but wouldn't that only be if the array value is like in chronological order like this?
Yes, it only works on sorted arrays. But the thing is, there are very, very efficient sorting algorithms. We are not learning them. We are learning the basic sorting algorithms. It might actually, in some cases, when you come to large data sets, make more sense to sort the data set and run a binary search instead of performing any other a linear search there, right? Because it is actually going to be way more efficient in terms of being able to in terms of steps and comparisons. And we'll talk about something a little later called Big O notation, which kind of explains this in detail when we get into sorting. But you know, this is a very efficient sort as compared to the linear, sorry, this is an efficient search, sorry, as compared to the linear search. It actually almost always takes less time on average to find a value when you are doing a binary search. Let's see what happens when our search key is not in an array. Okay, so when our search key is not in an array, so let me see if I could just copy this. I'm gonna copy these. Oh, why aren't you selected? Oh. All right. So let's say we have the same array, but let's identify a value of 20. Okay, so let's say, for instance, our key in this instance is 20. And of course, by a quick glance, we could tell that 20 isn't here. But let's see what are the conditions for stopping this search if it is that the search key doesn't exist. So again, we start off with the start value at 0, the end value at the last position, 12, and the middle value will be 6 because 0 plus 12 divided by 2 is 6. And we see here right off the bat that the value that we're looking for is bigger than the middle value. So we know right off the bat that our value here doesn't exist in this first half, which means that we have to have a new start value starting at the one after the middle value. And 7 and 12 is 19 divided by 2 is 9. So we have this middle value here. And the middle value is bigger than 20. So we know that from here go forward, we don't have any values inside of there. So we can remove this, we could remove this. And the new end value will be here, right? Start and end. Start and end. 7 and 8 is 15 divided by 2. So the middle value is going to be here. 21 is larger than 20. So we know that this is not it, and anything bigger than it is not it. So what is going to happen here is that the end value is going to end up here. But what happens is that the end value is now before the start value. And if the end value is before the start value, that means that you have negative amounts of values to search. And that means that there is no possible values left for you to search in the array. So it means that no value exists. So the condition for finding out when the search key is not in the sorted array, the condition for finding out that the search key is not in the sorted array is when the end value index is smaller than the start value index. Are you all with me?
Yes, sir.
Yes. All right. Okay. So let's see if we could define this. The definition for this one is going to be a little longer than the definition of the linear search array. All right, so we can say in a binary search, the start and end values, right, or start and end index values are marked and a middle index value is determined by adding the start and end index values and dividing dividing them by 2. Okay, that's what we did just now. We have the start value and the end value, and then we take those two and we take the middle index value by dividing them by 2 when we add them up. And we compare, right? Compare the value placed in the search key against the value, or let me see, against the element value at the middle index. Now we have to do something depending on the value of the middle index. If the middle index value is smaller than the search key, if the middle index value is smaller than the search key, what does that mean? Right? It means that nothing before that middle value can match the search key. Right? It means that nothing before the middle value can match the search key. And this means that a new start value should be assigned the index value after, let me put this, right, to the index value after the current middle value. So you all understand, that's what we did just now. If the index value is smaller than the search key, it means that nothing smaller than that middle index value is going to be the search key. So we can write off a half there, right? A half of the array one time. And then it means that we could start searching from the value immediately after the current middle value. So we do the same thing for if the middle value, if the middle value is bigger than the search key, right? If the middle index value is bigger than the search key, it means that nothing after the middle value can match the search key. And this means that a new end value should be assigned index value before the current middle value. All right, and I'm going to also put start in all caps here and end in all caps here, so that you know that these are different in that manner, right? Repeated is repeated, or let me say the above is repeated until somebody has a question? No? So the above is repeated until either the middle value matches the search key or end value, right? The end index value falls to below the start index value. And we saw it in this case here, right? In this one, it ended up being that the middle value matched the key value. In this one, it ended up being that the end value, the end value fell to less than the start value. Are you all with me on that? You all with me on this? Yes, I see Alicia, yes. Thumbs up. Hazard saying yes. All right. All right. So here's what we're going to do. I'm going to walk through this one with you all quickly, right? I'm just going to populate an array with some values that go up in increments of 3 or something. So, and then later on we will learn the search, and then we will come back and apply the search, and then apply the search and then apply binary search to apply the sort and then apply a binary search to the sorted list. Okay, so allow me to switch to code blocks. Actually, just let me do the whole window screen. All right, so we're going into code blocks and we're going to start a new file, and we're going to name this file binary.c. Right, I'll name it simple binary.c because this one, is you know, it's just really basic. So this one is just a simple binary search on a list of a particular size. Okay. So int main. What we're going to do is that we're going to, I'll put up the specification here. Allow a user to enter the size of the array that they wish to apply a binary search on. The user will also enter an increment value for the array and a start value for the array. Okay? The user can then search through this array by entering a key, and a binary search will be performed to state if the key value that the user entered is found. Okay, so the user will enter the size of the array, so the user can enter array up to you know, whatever size. Let's assume up to let's say 1,000 or 10,000 or something. So nothing too ridiculous, right? They could search that array by entering a key, and the binary search will be performed on that array. So they will enter what value was the first value in the array, how much each value will jump up by. So if they enter 10 and they say that each value will jump up by 2, it will be 10, 12, 14, 16, 18, up till how much ever the size of the array that they want. Okay? So we can have an array of size, let's say int let's say 1,000. Let's assume that they're not making an array bigger than 1,000. They could put the user increment and what is that third value that we want from the user? The start value, right? The start value. But it will always go up from there. So let's set this up and then we'll set up the array business, okay? So we could say printf, and we are saying printf, and we are going to say please please enter the size of your array. Okay, so if we want for, like 10 values, 15 values to move up, whatever, that's what we're going to use, right? Please enter the size of your array. So, all right, R underscore size. So let's say we get scanf, right? Percent sign D, ampersand R underscore size. Everybody with me so far? So this array, the person want 15, if person want 15 values in it, right? And we could say then, let's just copy and paste stuff because we want to move fast. Right? Please enter the size of your array. Please enter the what? The start value for your array. And we're going to put that inside of start value. So we say ampersand value. And then we are going to please enter the increment of your array. Increment for your array. Okay. And then we're going to say increment the size. How are we going to do this? We're going to say we need a counter for a for loop. So we could use I as a counter. We could say for I is equal to 0, right? For I is equal to 0, right? For I is equal to 0, semicolon, I is less than array underscore size, semicolon, I plus plus. So if for every value up to the size of the array, for every value to the size of the array, we want to set that first value. We want to say array at position I is equal to the start value. Okay. So, well, let me actually do this outside here. Array at position 0 is equal to, so the first value inside of the array is the start value. Okay, and then when we say value, we will say that that value up to the size of the array is going to be the user increment plus the previous value in the array. All right, so we say array at position I is equal to array at position I minus 1 plus user increment. Everybody understand? So for every value up, so we set the first value in the array to the start do? We will say printf, put a space between them, %sign D, and we'll print out array at position I. Setup. We just set up the CD values in our array and make sure that we have an array sorted according to increment. Okay, so please enter the size of your array. Let's say we want 20 values in this array. Enter the start value of your array. We want to start at 34 and the increment is 7. Okay, so our array goes up in ascending order, and this is the perfect array to be able to perform a binary search on. Do you agree? Great. Oh my gosh, I don't know why I'm cracking up over this like this, right? Nobody answered and I still said great. Anybody, are you all hearing me? Joshua, okay, I'm coming through a little.
Yeah, so yeah.
Poorly.
Yeah, so yeah.
All right. All right, good. So we set up our array. Okay, and remember, now we want to have the binary search. So let's int start, comma, end, comma, middle. Okay? These variables here for our binary search. And we also need the search key. So let's ask the user, right? So printf. Next thing is please enter the search key value you wish to find. Okay, so please enter the search key value you wish to find, and the name of that variable is key. So we're going to scanf, $sign D, and we'll have ampersand key. So we have please enter I didn't put my get jars up here either. I know that before we used to get some problems when we didn't put the get jar after the scanf. So we're doing that now. So please enter the search key value you wish to find. Scanf, %sign key, good. So we have that. So now what do we want to do? We want to say that the start index needs to be at 0. So start is equal to 0. The end is equal to, right, the array size minus 1. Array underscore size, right, minus 1. Yes, right, because this is the last position in the array. And so the middle value is going to be start plus end, start plus end divided by 2, and it's an integer division, right? So we don't want any half point, floating point numbers or anything like that. So the start value, the end value, the middle value. That's what we do it. And what do we do? We know that we want to loop until a certain criteria is met. What is the criteria that is met that we want to loop? We want to say while what? End is larger, bigger than or equal to start. You all understand why I'm doing this, right? Because this is we don't want from our example, where we go back to the example, the condition for stopping hinges on you know, start always being smaller than end. So while end is less than or equal to start, what do we want to do? right? And actually we could put this statement inside of here. The first thing that we do is we find the middle position. We find the middle position. So once the start value is smaller than the end value, what do we do here? We say set the middle position, the middle index position, okay? And then we want to start comparing. So we said in our definition that if the array at position middle is larger than, if array at position middle is larger than the search key, what do we do? If it is that the key, right, or let me put this around the other way, it might be, if the key is bigger than array at position middle, what does this mean? It means that middle or nothing smaller than it can be considered. So it means that we need to take start and say start is equal to middle plus 1. Okay? So if the search key is bigger than the middle index value, set the new start position to after the middle. Okay? Right? If, right, we go with an else. Else if the key is smaller than array at position middle. What does this mean for us? It means that if the search key is smaller than the middle index position, then it means that there is no way that we could find the search key anywhere after the middle position. So we need to say end is equal to middle minus 1. Right? And else, well, I mean, if all else fails, it means that the key was found at this position. Okay? So maybe we should have a value called found to record the position where it was found at. So we could say found is equal to minus 1. So minus 1 doesn't exist in an array. So if it is that the key was found, we could say found is equal to middle. And this is what will loop until we either, and then we could say break the loop. Okay, so else, meaning that the key was found at the middle position and stop the loop. But if it is that if we reach the end of the loop without it being found, it means that we could do this. We could say if found is equal to minus 1, it means that we should printf that the key was not found. Otherwise, else, we could printf the key was found at position %d. And we print out this found position here. So hopefully this works. The code is actually way simpler than you think. Okay? So if at the end found is minus 1, then print not found. print the position where it was found. So let's test this and see. Okay, let's test it and see. I hope that I got everything right. Enter the size of my array. My array is 10. Enter the start value for my array. The start value for my array could be 2, and the increment could be 2. So we have 2, 4, 6, 8, 10, 12, right up to 20. Enter the search key value I wish to find. Let's look for 16. 16 was found at position 7. Okay, now let's check and see if we have a value that doesn't exist inside of here. And let me go and fix my, I need to print out a \n here, right? So again, let me see, enter the size of your array, 15. Enter the start value for your array, 60. Enter the increment for your array 1. So I go up from 60 to 74. Please enter the search key value that you wish to find, 88. With values of ascending order. Okay, so let's do a big array. Let's say we have a 500 size array. Enter the start value, 26. Enter the increment, 17. Okay, so we have a bunch of values here. Let's see if we could find a value, right? 6,240. Okay, look, at position 364, 6,214 was found. Let's see if I could find it in the list. 6,214, right here. Okay. So your binary search is a nice, reasonably quick search for even larger lists. Okay. We went through the binary search, we went through the linear search. We spoke a bit about the limitations of the linear search as opposed to the binary search. The linear search could work on any unordered list, but it's not very efficient. The binary search could work on an ordered list only, but because of its divide and conquer approach, right? Because of the fact that my list is huge, after the first search, it cuts that amount in half. After the second one, you're searching a quarter of the original list. After the third one is you're searching an eighth of the original list. So if your list was size 1,000, on the second search you're searching 500, on the third search you're searching 250, on the fourth search you're searching 125. You see how it slims down? In 4 steps, you cut out 750 locations that this value could not possibly be in. Okay, so anybody have any questions before we call it a day? What I have to give you, students, is that you're consistent. All right, I like that. We have some consistencies. I hope that everybody, Ryan done waving goodbye. Ryan, I was like, I have no questions. I'm ready to leave. Bye-bye. Okay, so that's fine. I hope that everybody had a good session. If we have no questions, then we can say adios.
Yeah, bye, sir.
Yeah, bye, sir.
Bye.
Yeah, bye, sir.
Bye. Bye. All of a sudden, I hear people talking.
I might see you in school later if they're still there.
Yes, I will be here until about at least 2 o'clock.
Well, yeah, I'll see you.